Hi, everybody, and thank you for joining us today for our webinar, Considerations for Thin Blanket Insulations. I'm Kim Melton, and I will be your moderator and co-host for today's presentation. But before we dive into introductions, however, I did want to go over a few logistics. First off, if you have any questions, you can submit those throughout the webinar, and you can submit them to our panel at any point during the presentation via the Q&A feature. Our host and two members of the JM technical team will address these questions live at the end of the presentation. Now, if you don't see a Q&A option to the right side of your screen, look for the series of circular icons at the bottom in the middle of the screen and select the icon with the ellipsis in it. And it will open a menu option with a Q&A at the top. So if you select that option, and it will open up a dialog box there on the right side of your screen that you can use to submit questions at any point during the presentation. Now, we'll follow the webinar today with a survey, and this is your opportunity to provide us with feedback on how we did today, ask any questions you may have about the topic of the webinar, or even suggest new topics for questions or topics for webinars, that you'd like to hear in the future. We're continuously striving to improve and evolve our webinars, so if you have any comments or suggestions as to how we can better accomplish this, or maybe even if you feel like we've missed the mark today, we'd encourage you to fill out the survey and give us your feedback. We'll use this feedback to improve our webinars and provide information that has the most value to you in the future. Now, this is part of how we deliver the JM experience to you, and the JM experience is based on 4 pillars of the JM culture, and that's people, passion, perform, and protect. And we believe it's critical to make sure that we hear and understand and respond to your needs in order to deliver the best interaction to you. So we often offer webinars like this one to help educate the market and offer a tool and a resource for you and your business. But we understand that this isn't just a one-way street, so your feedback is a key component to helping us evolve to better meet your needs. Now, we're also frequently asked whether or not we send out these presentations upon their conclusion, and we don't actually send out the presentation itself, but we do post a recording of it online for you to watch at your leisure or share with your colleagues, and this ensures that you can have the presentation within its full context. So with that, we're going to get into some introductions. Joining me today are Jeff Semkowski and Kelly Sandin, and they're going to kick us off with an introduction.
Okay, thanks, Kim. I'm Jeff Semkowski, a proud Canadian and recently relocated to Johns Manville's world headquarters in Denver, Colorado. I lead Johns Manville's industrial portfolio. I've had the pleasure of working at JM for 6 years in both sales and product line leadership roles. I have 12 years experience in the industry in a variety of roles, primarily in the construction and building materials segment.
Thanks, Jeff. Hi, I'm Kelly Sandin. I'm the Corporate Industrial Hygiene Manager here at Johns Manville. I have been at JM for 8 years. I am also a certified industrial hygienist, and I have 28 years in the occupational health and safety arena.
Thank you, Kelly. And again, I'm Kim Melton. I am a technical editor here at Johns Manville. I've been here for 4 years, and I am responsible for developing and managing all of our technical content for the industrial, HVAC, and mechanical businesses. And with that, I'm going to turn it over to Jeff, who's going to get started.
Okay, thanks again, Kim. As we get into the presentation, I sort of want to preface the agenda and remind our audience that the purpose of this presentation is to educate you on some of the many technical considerations which should be top of mind when specifying and utilizing thin blanket insulations in your facilities. So consider each section like a separate technical presentation, which should each play a part in your decision-making criteria when working with these materials. I'm going to start with an overview of 2 common types of thin blanket insulations, and then where they can be used, and then we'll discuss the thermal performance of each. Kim will then present 2 modules. The first one's going to be on high vibration environments, and then the next one is on corrosion prevention. Then the final technical presentation will come from Kelly, who will discuss recent testing we completed on dust as it relates to thin blankets. So now we're going to talk about the prominent thin blanket insulation materials commonly utilized for industrial mechanical piping, tank, and equipment applications. The first material I'm going to talk about is InsulThin HT. InsulThin is a thin blanket offering from Johns Manville's Industrial Insulation Group, which was first introduced into the market in 2014. It is a highly efficient insulating material, hence being categorized as thin. InsulThin is intended for applications with operating temperatures between ambient and 1200 degrees Fahrenheit, and is currently not considered a solution for the sub-ambient, or what's commonly referred to as the cryogenic market. InsulThin is comprised of microporous insulation materials reinforced with glass fibers and encapsulated in a needled e-glass fabric. It's a quilted product, meaning it is stitched throughout the blanket. InsulThin is easily fabricated and installs quickly in numerous applications. It is also important to note that InsulThin is a hydrophobic insulation, meaning it does not absorb water. InsulThin is typically sold in rolls and manufactured in 10 millimeter and 5 millimeter thicknesses. So let's move on to the other common thin blanket insulation material, commonly known as aerogel blanket. Like InsulThin, the common temperature range where aerogel blankets are utilized is ambient to 1200 degrees Fahrenheit. However, there are certain aerogel product offerings which can be used in cryogenic applications when the material is manufactured with specialty facings. Aerogel blankets are more of a felt-like material. They are hydrophobic and can also be fabricated for piping, equipment, or tank applications. Aerogels are typically sold in rolls, and also like InsulThin, the most common thicknesses are 5 millimeters and 10 millimeters. So I've briefly mentioned some high-level applications where thin blankets can be utilized, but now let's talk about some of the most optimal applications where these materials can be installed. The first place where thin blankets make really good sense is confined spaces. I'm sure many of us attending this webinar can think of a cringeworthy example you've seen in your career where pipes or equipment were built and then the insulators need to come in and install 3 inches of insulation material in a 2-inch clearance, or even worse. Installation expectations can sometimes be impossible or downright crazy. Thin blankets are highly efficient insulators, meaning less material thickness than traditional insulation materials is required. Thin blankets are ideal for applications where there's little to no room to insulate due to space constraints. The next way we recommend using these materials would be in what we call hybrid applications. And this means installing InsulThin in conjunction with other traditional insulations such as calcium silicate, perlite, or mineral wool. A great example I can give is when mineral wool is specified on high temperature applications. As most industry professionals are well aware, mineral wool experiences what is often referred to as binder burnout, which can begin when exposed to temperatures above 300 degrees Fahrenheit and can lead to a calamity of problems in an industrial environment. A hybrid solution will allow the majority of the insulation thickness to remain mineral wool in order to achieve cost savings, while the inner layer of hydrophobic thin blanket insulation can lower the interface temperature between the hot pipe or equipment and the mineral wool, preventing binder burnout and all of the potential problems associated with it. Another prominent application is high vibration environments. Again, with mineral wool binder burnout in a high vibration environment, the structural integrity of the material, especially in piping applications, can be compromised, causing material sagging on the pipe, which can dramatically affect the thermal efficiencies of the system and can allow voids in the jacketing, which could allow moisture in, which may cause corrosion. Thin blankets, when properly installed, significantly mitigate the risk of structural degradation in material due to vibration. Kim will expand on this greatly and show you some compelling test data detailing our superior performance of thin blankets versus traditional insulations in high vibration environments. Finally, I'll say that large diameter tanks and specialty equipment such as coker drums are an excellent application for thin blankets. The thin profile will reduce the overall size and footprint of the equipment, and the material installs quite easily when unrolled and applied to the walls of the drums, as the roll format can allow for installation of significantly more square footage of material compared to traditional materials or board products. And then also I want to mention, historically thin blankets have not been an insulation of choice for small diameter piping. However, unlike some aerogel products which require scored fabrication to fit around small piping, 10 millimeter InsulThin HT is flexible enough to install on pipe down to 2 inches in diameter. 5 millimeter InsulThin HT can be installed on piping less than 2 inches. Again, the majority of applications in the industrial thin blanket space are typically at temperatures above ambient, and mostly between 200 and 1200 degrees Fahrenheit, as that range in particular lends itself to significant thickness savings compared to traditional insulations. Now I'd like to change gears to a more technical part of our presentation and show you the thermal performance of thin blankets. And we'll start by first explaining the different ways used to measure heat transfer so we can properly understand the thermal performance of these insulations in particular configurations. This is absolutely critical in order to ensure a given system is specified with the correct and minimum insulation thickness. There are 2 methods which are commonly used to measure heat transfer and material thermal conductivities for thin blankets. One is for piping and the other is for flat configurations. ASTM C335 is the method used to measure heat transfer with material installed on a piping apparatus where the low temperature side is open to the ambient environment and multiple layers of material can be tested. The test method is reflective of real-world environment because with C335, you can see multiple layers of blanket can be installed without significant compression, and the external environment is ambient. ASTM C518 tests for flat configurations. In this test method, heat transfer is measured with material compressed between two surfaces on a heat flow meter. You can see that in the picture on the right, with temperatures that can be controlled on both surfaces, and multiple layers are often tested. If specifying thin blankets for piping applications, again, it is absolutely critical to use ASTM C335 material K values and not ASTM C518. C518 values for flat configurations deliver better thermal conductivity, and therefore using the flat K values for piping applications can very easily lend itself to under-engineering the insulation system. And it's possible to specify less thickness or layers of thin blanket than what is actually required to achieve safe-to-touch or thermally efficient system. So let's show you the data so you can see the real importance of specifying the correct ASTM surface geometry. As you can clearly see, for both Silica Aerogel blankets and JM's InsulThin HT, the thermal conductivities, or K values, are higher for ASTM C335 in pipe configurations versus ASTM C518 in a flat geometry. As you know, the lower the K value, the better the insulator. Thermal conductivities for ASTM C335 pipe configurations are 15 to 30% higher or worse than flat configurations. So be sure to use the correct data for your application. I should also mention for your reference, there's not necessarily an industry recommended standard piping diameter for when to begin using flat versus round K values in engineering your insulation system. However, many major end users and engineers often use 48 inches. For reference, it should be noted that the ASTM standard for microporous thermal insulation is C1676 and can be referenced when specifying microporous materials like InsulThin HT. It is also important to note that ASTM C1728 is the standard specification for flexible aerogel blanket insulation. We encourage the specification in engineering communities to, of course, use these specifications when considering thin blanket materials. In reviewing the aerogel spec in particular, you'll notice that the leading materials K values are right on the line of the ASTM requirements. Any further impact or degradation to the product could put a system at risk for being under-engineered. The bottom line is to, of course, always ensure you're using the correct data to specify your insulation thicknesses. Know when to use C335 versus C518, and be cautious as not all material data sheets publish both pipe and flat data. For reference, you can see the InsulThin data sheet publishes both pipe and flat data in this slide. So now I want to shift gears a little bit and talk about an interesting phenomenon known as thermal shift. And I'm sure many people on the call have already seen a presentation or two on thermal shift, but we'd like to redeliver it again today. Thermal shift is a phenomenon that only occurs in aerogel products when exposed to high temperatures. So thermal shift is the permanent change of an insulation's thermal conductivity due to exposures to high temperatures, and this change tends to begin at 300 degrees Fahrenheit. Again, thermal shift has only been observed in tested silica aerogel insulations, and the shift is time and temperature dependent, meaning higher temperatures and exposure times can cause more degradation to the material's thermal properties. Data for calcil, perlite, mineral wool, and microporous insulations does not show thermal shift. So what does this mean for specifiers and end users currently utilizing aerogels? Well, because of the uncertainty in the degree of thermal shift, it is harder to confidently complete engineering calculations for thermal performance, safety, and heat loss with inaccurate thermal conductivities. Without factoring in a degree of material degradation and thermal shift for aerogel applications with process temperatures above 300 F, facilities may be at significant risk for under-engineered insulation systems, which could cause several potential issues. So to further explain thermal shift, we will show you what it looks like up close. As you can see, after the first heat-up cycle, there is a difference in thermal conductivity in the second cycle after initial exposure to time and temperature. So which line do you use? Notice the second cycle after thermal shift is above the ASTM C1728 specification maximum for flexible aerogels. You can see in the picture there on the right that the temperature breaks down the aerogel structure from large to small pieces and therefore reduces the air pockets that provide that great insulating value and thermal conductivity performance of the material. It is permanently affected. So how do you ensure you account for thermal shift? Quite simply, the aerogel system will require additional layers. and this needs to take place in either the design phase or after installation. As you can imagine, this can come with a significant cost and implications to your system, either at your capital or maintenance programs. Let's look at an example that brings everything I've just presented together. We will use a 12-inch pipe with an 800 degree F process temperature, an ambient temperature of 75 degrees Fahrenheit, with a wind speed of 2 miles per hour. The goal is for a thermally efficient system, also meeting the OSHA safe-to-touch temperature requirement of 140 degrees Fahrenheit. First, recall the importance of using flat versus pipe thermal conductivities to design your system. Notice it requires 55 millimeters or 6 layers of aerogel insulation as opposed to 45 millimeters or 5 layers if you were to utilize C518 flat thermal conductivities. Remember, some data sheets only publish the flat values. Next, notice the impact of thermal shift on the system. After the first cycle, the system would require an additional 10 millimeters or 1 layer of aerogel blanket to maintain thermal efficiencies and safe-to-touch temperatures. Also notice, if the system was originally designed using flat K values and not accounting for thermal shift, it would be significantly under-engineered by approximately 20 millimeters of insulation thickness, which is 2 full layers of aerogel insulation. This would not be a good situation. So my message to engineers, specifiers, and owners is always ensure you're using the correct data when specifying thin blanket insulations, and always remember thermal shift if you're considering using aerogel technologies. Now I'm going to pass it back to Kim.
Great, thank you so much, Jeff. So Jeff just took us through what we need to consider in terms of thermal performance, and one component that can play into thermal performance is vibration. Now, in materials with binder, like he mentioned earlier, like mineral wool, the binder burns out at higher temperatures, and this threatens the structural integrity of the insulation. But in high vibration environments, this can actually cause the material to sag or shift, and this in turn changes the insulation's thickness and ultimately impacts the consistency of the insulation's thermal performance. So neither InsulThin HT nor Silica Aerogel have binder to burnout, but as Jeff has already explained, InsulThin HT is a quilted product with fumed silica particles between the needle E-glass fabric layers. And this has led the question about whether or not the material between the needle E-glass fabric will shift and settle in a high vibration environment, having a negative impact on the insulation's thermal performance. Now, this is an excellent question, and we decided it needed to be tested. However, there's no ASTM test method that specifically tests for resilience to vibration. So what we did is we adapted ASTM C411 to meet the needs of this test. And what we did is ASTM C411 measures the temperature performance and sag resistance in mineral wool. And we used this test method and added an additional vibrational component to it to establish whether or not InsulThin HT would begin to sag or shift in an environment with excessive vibration. Now, we use the mineral wool standard for sag resistance, which is plus or minus 5% thickness and variation, to give us a baseline for what the industry would deem as like an acceptable amount of sag. For the test itself, we installed 2 layers of 10 millimeters of InsulThin HT on an 8-inch pipe and jacketed it, and then we conditioned the assembly at 600 degrees for 24 hours. After this, we vibrated the assembly at ambient temperatures for 100 hours, taking measurements at the top and the bottom of the assembly every 3 hours throughout the test. So here's a glimpse of what the results were. And at first glance, your initial thought may be this looks like a lot of variation. However, if you notice the red bracket on the right side of the screen, you'll see that from the top of the red line to the bottom of the red line is only 1 millimeter. So the majority of the variation in insulation thickness was actually less than half a millimeter, and even the most extreme variation throughout the entire test didn't actually exceed 0.6 millimeters. So keeping that perspective in mind, you can see the fact that there is relatively little vibration in the thickness of the top, that's the purple line you see there, and the bottom, the blue line of the insulation. Additionally, you may also notice that the insulation thickness of the top and bottom changed inconsistently, sometimes growing and sometimes shrinking. If the material were beginning to sag, we would have expected to see the top shrinking and the bottom growing in thickness, but that's actually not what happened here. So the takeaways you want to keep in mind are that the thickness varied between 21.7 millimeters as a maximum and 21.1 millimeters as a minimum. And as I said, the maximum variation throughout the entire test was only 0.6 millimeters. Now, if we compare this to the standard reference for mineral wool that I mentioned earlier, that's a plus or minus 5% variation in thickness, we find that InsulThin demonstrated plus or minus 1.5% deviation from the average thickness. This is really low variability and substantially less than the 5% variation allowed in the mineral wool specification. Again, the top and bottom did not shrink and grow consistently, which would have been expected if the material were experiencing a shift or beginning to sag as a result of the vibration. Now, given the relative lack of variability in the thickness of InsulThin HT throughout this vibration test, evidence suggests that InsulThin HT will maintain consistent thickness in a high vibration environment and subsequently will also maintain consistent thermal performance because the thickness is not varying. Now, we're going to shift away from looking at thermal performance and actually look at how thin blankets can impact corrosion under insulation. And I'm going to dive into some of the things that you need to consider in terms of designing thin blankets to help defend against CUI. So InsulThin HT and Silica Aerogel are both hydrophobic insulations, meaning that they won't absorb water. Unlike insulations like cellular glass, which is inherently hydrophobic, InsulThin HT and Silica Aerogel are made to be hydrophobic by a silicone-based hydrophobic agent that is added to the product chemistry during the manufacturing process. Now, this hydrophobic agent will begin to oxidize and burn off about 450 degrees to 600 degrees Fahrenheit. At these temperatures, the longevity of the hydrophobic agent is based on time and temperature, similar to thermal shift. So the hotter the pipe and the longer the insulation is exposed to it, the more rapidly and thoroughly the silicone-based hydrophobic agent will burn away. Once the hydrophobic agent is gone, the insulation may at that point absorb any water that infiltrates the system. Now, when water infiltrates the system and is absorbed by the insulation, it introduces the third and final ingredient that the system needs for there to be corrosion under insulation, and that's water. So as you can see here in this little trifecta, what we're looking at is three different variables: unprotected metal, oxygen, and water with a corrosive chemical or compound. Now, when the insulation gets wet, it holds that water and any corrosive chemicals in the water next to the pipe surface. Now, even more importantly, the chemical makeup of the insulation itself can also influence the rate and type of corrosion that occurs on the pipe surface by contributing to or inhibiting corrosion. Because of this, each insulation is measured to determine its corrosive potential so we can establish how it's going to behave and how it's going to influence corrosion on the pipe surface when water infiltrates the system. And we measure an insulation's corrosive potential as the mass loss corrosion rate using ASTM C1617. Now, ASTM C1617 is a method that generates an accelerated representation of corrosion on carbon steel, and it's designed to perform an analysis of the corrosive potential of the insulation. This method uses a leachate from insulation materials dripped onto a hot carbon steel coupon for 96 hours. After the test is complete, the metal coupons are cleaned to remove any corrosion byproducts that formed over the course of the test. The mass of the coupons before cleaning is compared to their mass after, and this difference between the two is known as the amount lost as a result of corrosion, and that is actually what's known as the mass loss corrosion rate, or MLCR. Each material's MLCR is then compared to the MLCR of one of three control substances. The first control substance is deionized water, and it's the least corrosive. The second control substance is 1 part per million chloride solution, and the third is 5 part per million chloride solution, and that's the most corrosive control substance. The standard specifications for each material that Jeff mentioned earlier are based on one of these three control substances, MLCRs. So InsulThin's standard specification states that it must be less corrosive than deionized water, while Silica Aerogel's standard specification states that it must be less corrosive than 5 parts per million chloride solution. Now, this can make it challenging to compare the two products if you're looking at whether or not they meet their standard specifications, because they both do, but the specifications themselves have different passing requirements. In order to establish a method that allows us to compare these materials side by side, we created the graph that you see on your screen right now. And the x-axis is the ratio of the insulation's mass loss corrosion rate to the mass loss corrosion rate of deionized water, the least corrosive standard reference. The number on the top of each bar represents each material as a fraction out of 1, where 1 represents DI water's mass loss corrosion rate. In this analysis method, the insulation's MLCR as a ratio of DI's MLCR is not actually written into the ASTM C1617 test procedure. This is something that we've provided as a baseline of comparison so you can compare the insulation materials with each other. Now, in this graph, the higher the ratio, the more corrosive the material is to carbon steel. And so you can see, starting from left to right, you're looking from least corrosive to most corrosive. The data there that's circled in yellow Those are the thin blankets, and InsulThin is the one on the farthest left, and it is about half as corrosive as deionized water in this table. And then the two Silica aerogel products that were tested, you can see they're about 2.25 to almost 3 times more corrosive than deionized water. So while both of these materials pass their standard specifications, it's clear in this graph that they don't actually demonstrate the same corrosive potential. InsulThin HT is less corrosive than the tested Silica aerogel blankets. So while ASTM C1617 is one of the more common standard test methods for exploring the corrosive potential of an insulation, industry end users actually felt that this short-term laboratory testing was too isolated and actually insufficient to get a full picture of the corrosive potential of an insulation and the longer-term performance of insulation in terms of CUI. So what happened was industry end users partnered with NACE, the National Association of Corrosion Engineers, to develop a relatively new test protocol, and this is NACE TG 516. And this test protocol explores the long-term performance of an insulation as a component of a complete assembly. That's the insulation, the jacketing, and the pipe. And the intent here was to design a test that could more accurately replicate real-world conditions in a laboratory setting. So NACE TG 516 tested fully insulated and jacketed pipe assemblies in highly corrosive conditions for 6 months. Each assembly was insulated with either InsulThin HT or Silica aerogel and jacketed and then exposed to one of two conditions. The first were sweating conditions. They kept the assemblies wet at 45 to 65 degrees for 6 months. The second conditions were cycling conditions, and these were conditions where the insulation was cycled between ambient temperatures and 600 degrees Fahrenheit. And between each cycle, the assembly was fully immersed in a tank of water. Now, for both conditions for the first 2 months, only tap water was used to wet the material, and in the last 4 months, they used a solution of 1,500 parts per million chloride. So in the cycling conditions, the elevated temperatures dried the insulation between each cycle, creating wet, dry, high temperature, low temperature conditions with a fair amount of variation. After the tests were complete, the insulations were removed and the pipes were cleaned to remove any corrosion byproduct. In the sweating conditions, researchers found that the corrosion depths and wall loss on the pipes were similar between both products. In the cyclical conditions, however, the products varied substantially, and as you can see in the right column at the top table, the mean corrosion depth of InsulThin HT after 6 months was 213 microns. The tested Silica aerogel blanket had a mean corrosion depth of nearly 1,400 microns. So if you're looking at it as the comparison, the mean corrosion depth of InsulThin HT was about 80% less than that of the tested Silica aerogel blanket. Now, when we look at the results in terms of wall loss, that's the table on the bottom there, and pitting, we find that the tested Silica aerogel blanket had the deepest pitting as well as the greatest wall loss, and that's in the third and fifth columns here that you can see those numbers as well. Now, the measurement results from the data can actually be seen clearly in the images of the pipes themselves. So the pipes on the right were the sweating conditions, and as is consistent with the data, they both look pretty similar in terms of corrosion on the pipe surface. On the left, however, we can actually see that the cyclical conditions, those are the pipes that were in the cyclical conditions, and you can see that the pipe beneath the Silica aerogel on the bottom left has substantially more and deeper pitting than the pipe that was beneath the InsulThin HT insulation, and that's on the top left there. Ultimately, researchers found that the results from the ASTM C1617 test method were similar to the outcomes of the NACE TG 516 test. Both tests demonstrated that InsulThin HT outperforms the Silica aerogel blankets it was compared to in terms of corrosive potential. NACE TG 516 also showed that InsulThin HT has lower corrosion rates and shallower pitting than Silica aerogel blankets that were tested. And you can see that here in the close-up image of the pipe surfaces. The deep pits, like the ones associated with Silica aerogel in the testing, you can see that here on the right side of your screen. That large black circle is a deep pit. And those are specifically what you want to avoid when it comes to corrosion. These types of pits are the ones that eat into the pipe wall, they threaten the structural integrity of the pipe, they create weak points and possibly even holes in the pipe in worst case conditions. So as you go about designing and specifying a thin blanket insulation, it's important to keep these results in mind by designing a system with the corrosive potential of the insulation in mind. If you know that your system will be operating at temperatures above 450 degrees, where the silicone-based hydrophobic agents will be likely to begin burning off, then selecting a material like InsulThin HT might be a more appropriate measure to take to ensure that you're designing a system where the insulation is less likely to contribute to corrosion if the system itself gets wet. However, This means addressing CUI in the design phase. Now, if you design a system under the assumption that water infiltration will eventually be an eventuality rather than a possibility, your system will be much better equipped to handle water infiltration in a manner that helps prevent CUI. And throughout the industry, there are practices that many facilities have put into use to facilitate faster drying times when water actually does penetrate the system. And we've taken a close look at the efficacy of some of these methods used to protect systems against CUI once water has entered the system. And these two methods specifically include using weep holes and adding additional layers of insulation. Now, two important things to note here. First, we always recommend replacing saturated insulation as soon as feasibly possible. This allows you to inspect the pipe beneath the insulation, helps prevent corrosive substances from being held next to the pipe surface for extended periods of time. Additionally, saturated insulation is substantially more thermally conductive than dry insulation, and it will significantly hinder your process control until it is dry. Second, while we will be discussing the results of recent testing done on weep holes, we don't endorse the use of these practices without the proper engineering analysis for your application and your system. So with that, let's take a look at exactly what weep holes are and what they do. The picture on the left is a weep hole drilled into jacketing. Now, a weep hole is simply a 1/2 inch to 3/4 inch hole that's been drilled into the jacketing, and it's on the bottom side of the pipe, and it allows water to escape once it's entered the system. The reason for this is that even though the insulation might be vapor permeable, and even hydrophobic insulations are vapor permeable that allow the water to escape, the jacketing is not. And so if the insulation gets wet, the heat of the pipe will certainly drive moisture away from the pipe surface, but it actually gets caught between the insulation and the jacketing without a means to escape. At this point, the water is actually held within the system, increasing the risk of CUI, preventing the insulation from drying out, and substantially hindering the thermal performance of the insulation system itself. Now, the second picture is just a picture of InsulThin HT, and in this test, we looked at the influence of adding an additional layer of insulation, specifically InsulThin HT, to a system with weep holes to determine whether or not the added thermal value of dry insulation influences the drying time. Now, we ran this test on 3 different assemblies to determine the impact of weep holes and additional insulation have on how long it takes to dry the system and how long it takes the system to reach 600 degrees Fahrenheit. For the test, we soaked Thermo-12 Gold, and that's Johns Manville's legacy calcium silicate that's not water resistant. We soaked it overnight. We weighed it, and then we applied it to the pipe, and then we jacketed the system as a whole. We heated the pipe to 600 degrees for 96 hours. And we measured, in that time, we measured how long it took the insulation temperature to reach 600 degrees and how long it took the saturated insulation to dry. Now, as you can see here, there were 3 different assemblies that we tested. The first assembly had saturated Thermo-12 Gold, a layer of InsulThin HT, and weep holes drilled into the jacketing. The second assembly had saturated Thermo-12 Gold and weep holes without the InsulThin HT layer. And then the third assembly just had the saturated Thermo-12 Gold and the jacketing without any weep holes. As you can see in the graph, the weep holes played a significant role in facilitating both faster drying time and faster heat up time. The system with weep holes and the additional layer of insulation on the left took 24 hours to dry. The system with only weep holes in the middle of the graph took 55 hours to dry, while the system without weep holes did not dry before we halted the test at 96 hours. So the weep holes themselves reduced the drying time by at least 40%, taking it from over 96 hours to down to 55 hours. By adding an additional layer of insulation to the system with weep holes, we cut that dry time from 96 hours down to 24 hours, so almost 75% when you compare it to the system without weep holes. The weep holes obviously played a great role in allowing the system to heat up more quickly. As you can see, the test assemblies on the left and in the middle, they heated up 6 times faster, taking approximately 4 hours rather than 26 hours to reach the appropriate operating temperatures. Now, this test demonstrated that weep holes should be carefully considered in the design phase, as they could play an integral role in protecting the system after a major flooding or weather event. Adding additional layers of insulation, particularly a thin, flexible blanket like InsulThin HT, can also make a substantial difference in the insulation system's recovery time. However, again, these are components and strategies that should be carefully assessed and considered by a specifying engineer prior to implementing them on any system. So with that, we're going to wrap up corrosion, and I'm going to hand it over to Kelly, who's going to talk about the latest industrial hygiene sampling.
Thank you, Kim. So because of the dustiness of some products, some employers started requiring protective suits, respirators, workplace enclosures, and special cleanup requirements during the installation of different insulation products. And for that reason, we wanted to do an industrial hygiene test to determine the amount of dust that InsulThin HT produced versus the Aerogel thin blanket products. So for this test, we developed a installation where we did a 20-inch pipe and an 8-inch pipe, about 2 hours per pipe, and we did industrial hygiene sampling on the installer, and they went ahead and cut the insulation to size, wrapped it around the pipe, and then used typical installation techniques. And as I said, we sampled both the InsulThin HT and then 2 different Silica Aerogel products. And we measured the products for both respirable particulate and total particulate. And the difference between the two is respirable particulate in general are particles that are considered to be about 5 micron or less, and are particles that are small enough that can get into what we call the gaseous exchange region of the lung. And the respirable particulate, the total particulate includes the respirable particulate, and total particulate is basically any particulate that can be suspended in the air and is available for inhalation into the respiratory system. So you can see on the left of this graph, we have the results for the respirable particulates, and you can see that the results are reported in milligrams per cubic meter. So that's the amount, the weight of particulate per a certain size of air. And for the respirable particulate, you can see that the InsulThin HT was lower than the comparable aerogel products. And then on the right, we have the results for the total particulate, and you can see that the InsulThin result is actually significantly lower than the aerogel products. So for the results of this test, we found that InsulThin HT produced about 65 to 80% less dust than the 2 Silica Aerogel products that were tested. Of course, the environmental and work practice conditions where the material is installed will influence the amount of dust that is present in the air. And then JM always recommends that each employer wants to remind everybody that each employer is responsible for actually meeting the OSHA standards and whatever applicable occupational health standards for their jurisdiction.
Great, thank you, Kelly. So let's go ahead and wrap this up with some conclusions and a quick recap of what we've already gone through. As you've seen, there are a lot of variables that system designers need to take into consideration before selecting and specifying a thin blanket insulation, starting basically with the physical differences between InsulThin HT and Silica Aerogel. We're looking at InsulThin HT as a quilted blanket versus a felted blanket of a Silica Aerogel. And as Jeff mentioned earlier, on small diameter pipes, a quilted blanket may be a better option in terms of flexibility and handleability than a felted blanket, which is a little bit stiffer. You also want to make sure that you're accounting for the surface geometry of your application when specifying insulation thickness. This is crucial. You want to carefully check your product data sheets and make sure that the thermal data that you are using for your specifications matches the thermal data and the system requirements of your application. Also keep thermal shift in mind if you're designing a system with Silica Aerogel blanket insulation. Now, this can help ensure that facility operators don't have to go back and retroactively correct systems that have been installed but aren't performing as expected. Excuse me. Also, if you have a system that is insulated with Silica Aerogel and you find that it's running hotter than you expected, thermal shift may be the culprit, and that's something you want to consider as you decide how you're going to address your hotter temperatures. Now, you should also design the system with the assumption that water infiltration is an eventuality by considering the corrosive potential of the insulation materials that you select for your system. And you want to do this in the design phase. Keep in mind that even though each material passes its own standard specification, as you saw in that graph earlier, just because it passes a standard specification doesn't mean the performance is all equal. Each material has a different corrosive potential. And as demonstrated by NACE TG 516 and ASTM C1617, InsulThin HT has a lower corrosive potential than the Silica Aerogel products that were tested, even though both materials still meet their standard specifications. Also, as you're designing your system to prevent CUI, consider whether adding weep holes would be an appropriate step for your application. And finally, as you're dealing with industrial hygiene on the job site, Keep in mind that not all blankets generate the same amount of dust. Installers and facility owners and operators can help reduce the amount of dust generated by, on a job site by selecting a less dusty insulation material. Certainly, again, you are responsible for managing the OSHA requirements on your job site specifically. Now, if you're looking for additional resources on thin blankets, we do have a variety of tools available to you. The first one I'd like to talk about is our InsulThin resource page. Now, on this page, we have all the content we've developed regarding thin blanket installations in one spot. And this includes 4 new videos that address some of the information we've discussed here today, and they show you how to install InsulThin HT and discuss the handleability of the material. So you should, in your chat function, be receiving a link to this page right now that you can use to access a lot of this information. In addition to that, if you're looking for a detailed review of everything we've discussed in this webinar today, you'll want to take a look at the eBooks tab on the InsulThin resource page that we just sent you. Now, these eBooks are where you'll find the details of all the research that we've discussed and all the research that we performed on our thin blankets. And you can see the one here on the left. That's the comprehensive results from real-world corrosion under insulation test protocols. That discusses the NACE TG 516 test protocol. And the one on the right is considerations for thin blanket insulation in industrial applications, and it discusses all the topics we presented here today. Now, both of these ebooks are free, and they give you the complete results of all the testing. And you can use the same link we just sent you in the chat feature to get these ebooks and download your free copies today. Now, if you're looking for a broader information resource, I'd like to encourage you to visit the source. This is an online portal where you have free access to all of our blogs, recorded webinars, product documents, specifications, training, and tools. So when we look at our blogs, we're talking about content that we both write in-house at JM and we curate. So we go out and we find technical experts throughout the industry to help contribute to our blog. And these topics, they hit on targeted technical information, the latest news in the industry, scientific details that are critical to successful installation system design and operation. And we strive to make this content as rich and relevant as possible so that it can better serve you in the information that you need. Now, there's also a full library of helpful technical documentation on the source, and you'll find technical bulletins, white papers, and product application guides. So we strongly encourage you to browse this section if you're looking for detailed information about products or leading industry issues. In the tools section, you'll find tools like NEMA's 3E+ tool, and this is a tool developed by NEMA to help make specifying installation easier. What we've done is we've partnered with NEMA to use our the specs for our products in their tool. So if you know you want to specify InsulThin, for example, and you download this free NEMA 3E+ tool, it will give you the exact thicknesses you need of InsulThin HT insulation for your application or any of the other JM insulating products that you might want to use. We also have on the tool section an app you can download to your phone called the SmartBinder app, and this app gives you fast, easy access right from your phone to all of our data sheets and technical documentation. So there are other tools on there that you might also find helpful. And then finally, our webinars are on this on the source, and today's webinar will be recorded and posted on there, and we will send you a link when it's live. And so if you've missed any part of the presentation today, or if you'd like to review the webinar a second time, or maybe even feel the content might be relevant to a colleague, you can access this on demand online. Now, where to find the source? If you go to our industrial installation page, you'll find that there are 2 ways you can get to it right from the home page. You can either click on the spec tools, tech documents, webinars on demand, or you can actually click on this button on the right side of the screen that says the source. For everybody who attended today, you will receive a certificate of completion, and this will be sent to you by Friday. So with that, we are going to get started on some questions. In addition to Jeff and Kelly joining me today are Jack Bittner, JM Senior Product Manager, and Mary Beth Jones, a Senior Research Associate at JM. They're also on the line to help field any questions. And, excuse me, our first question is for Kelly, and that is, how does industrial hygiene sampling differ from installation in the field?
Yeah, so the sampling that we did for this installation, we tried to make the conditions very standardized for each particular installation. So obviously in the field, your individual air sampling results will vary depending on environmental conditions. For example, how windy is it, how big is the space you're in, and also individual work practices. So you really do need to do, for that reason, you really do need to do your own industrial hygiene sampling in the field, especially for OSHA compliance.
Great, thank you, Kelly. The next one is actually, will you be sharing the industrial hygiene data with us? And again, if you click on the link that we sent you in the chat box, you can actually get the industrial hygiene data all right there in the eBook about thin blanket consideration. So you can get that right there online and have it in your hand for reference as needed. And again, we will also post this webinar online so you can come back and reference the webinar as well. The next question I have, let's say, is for Mary Beth, and that is, why is InsulThin not recommended for cryogenic applications?
So for cryogenic applications, it needs to be a closed system, and right now there is not any system designed for InsulThin to be in a closed system, unlike the Aerogel product, which does have a system designed with a facer and a jacketing closure.
Thank you, Mary Beth. Jeff, the next one is for you, and that is there a maximum thermal shift, or is the thermal shift dependent on the exposure to time and temperature?
Thermal shift is dependent on exposure for time and temperature, and I should say that once thermal shift has happened, the material won't degrade any further until it's fully shifted. But so it is permanent, but the degradation does not continue after thermal shift occurs.
Great, thank you. The next one is for you, Mary Beth, and that is, how does the water leave the system with weep holes if the InsulThin is hydrophobic and would trap the water inside the covered wet insulation?
So that really comes down to how the InsulThin's installed. In order for the water to leave the system, you have to make sure that the seam is facing downwards where the weep holes will be so that the water can drain out of the system through the InsulThin, even though the material is hydrophobic.
Great, thank you, Mary Beth. The next one is for you, Jeff, and that is, can you use InsulThin in combination with another thicker insulation?
Yeah, in my part of the presentation when we talked about hybrid solutions, you can definitely use it with other insulations. Typically, my example was using it with mineral wool to help reduce binder burnout, but you can also use it in conjunction with calcil or perlite. A good example with calcil is if the engineers are looking for that structural rigidity and compressive strength of the calcil insulation, but want to minimize the overall thickness of the calcil solution, an inner layer of InsulThin would be a great option to help reduce the thickness, but retain an outer layer of rigidity on the calcil.
Okay, the next one is for you, Kelly, and that is, why do you monitor for both respirable and total particulates? Why not just respirable?
Well, you can look at the results from the data, and you can see that the results were different for the respirable and the total particulate. Also, OSHA has 2 different exposure standards for respirable particulate and total particulate. So it's pretty typical to actually monitor for both sizes of particles.
Great, thank you. And this information is actually also on the videos I mentioned on the InsulThin resource page. And that leads me to our next question, which is, what other key factors, in addition to those listed in this webinar, need to be considered for installation of insulation? All that information, you can actually find that on the InsulThin resource page in the videos. We have an example of the contractor, a contractor installing the material for you, talking about the components that you need to take in mind as you're installing the material. The next question I have is for you, Mary Beth, and that is, why did you only use tap water for the first part of the testing and then the chloride solution for the second part of the testing on the NACE TG 516 testing?
So that's really just to give multiple conditions to the system so that you can see the different variation in severity between the tap water and then the worst case scenario of the chloride solution in the water. Plus, the tap water comes to a steady state condition pretty quickly. So in order to mimic the most real world conditions, we like to test both the tap water and the chloride solution.
Great, thank you. Mary Beth, this next one is also for you, and that is, do you have any criteria or recommendation for weep hole spacing?
So we do not have any criteria or recommendations for that. We leave that to the engineers and the installers to use their own recommendations for those types of installations.
All right. The next question is, do you have any specific recommendations for handling procedures, cutting tools, installation practices, et cetera, to minimize worker exposure to particulate. And Kelly, I'm going to hand that to you one to just talk a little bit about the PPE.
Yeah, so I would definitely recommend that you, regardless of whatever system that you're installing, that you follow the manufacturer's recommendations, both on the technical documents and also on the associated product safety data sheet. Obviously, that to minimize dust production, you would want to not use an aggressive cutting method. You want to use probably the most simplistic cutting method that you could. And then you would definitely want to wear gloves or you can wear a protective suit just to protect dust from getting on your clothing. But all of those recommendations should be in the product safety data sheet as far as what PPE is recommended for the individual product and installation.
Great, thank you. So Jeff and Mary Beth, I'm going to pose this next one to you. I'm not sure if we have any data on this, so we may have to come back to this question, but if the InsulThin is applied to a tank panel system, will the adhesive change the K value of the insulation?
I don't really know how to answer that at this time, Mary Beth. I wouldn't think that the adhesive would change the insulation K value.
We don't have any data around that, so it's not going to affect the K value specifically of the insulation, but it may affect the overall K value of the system. And like I said, we don't really have any data to support that right now. That's something that we can look into.
Okay, and the next question is there a thin blanket insulation system that could operate between minus 20 degrees Fahrenheit to 450 degrees systems as the low and high? Are you guys aware of any material like that?
Well, you know, for the sub-ambient, like the minus 20 degree Fahrenheit limit, I would say probably there is an aerogel solution that is utilized for sub-ambient conditions with the specialty facing. Right now, InsulThin is only recommended from ambient, or sorry, not from ambient, from 0 to 1200 degrees Fahrenheit. So once you get above freezing temperatures, then that's where InsulThin is recommended.
Great.
Low freezing temperatures from a thin blanket, I think there's aerogel solutions for that.
So that wraps up the questions. There were a couple questions we actually were not able to get to based off of either information or content in the questions, and so we will reach out to you. If you've asked a question it wasn't answered, we'll reach out to you privately. But that wraps up our questions for today. So thank you very much for attending. We hope you found this information useful and relevant. If you have any additional questions, please don't hesitate to reach out to us directly, or you can do it via the survey that's going to pop up as soon as we close this webinar out today. You can take the survey to submit any questions that we didn't get to, or maybe you think of a question as we close out here. Otherwise, take care and enjoy the rest of your week, and have happy and safe holidays.